So where were we? We just started with 2D flows, right? 2D linear flows. And hopefully we will go all the way to the end of the 2D nonlinear flows today and see the most interesting thing that can happen in 2D when you go nonlinear. Okay. So we need to develop this classification of linear systems. Okay. What we are going to do is we are going to look at this matrix that we have, and its eigenvalues and eigenvectors will tell us what's going on. Let me just remind you that what we were doing is x1, x2. This is for the linear case. D over dt was some matrix times x1, x2. Do you remember this? Yes? And you might remember from the very first lectures that you can propose a solution like this, right? And if you do so, you can just substitute that into this equation and you end up with an eigenvalue equation, right? And the solutions will have a form of, the solution will have a form of C1 e to the lambda 1t plus C2 e to the lambda 2t. I forgot x1 and x2. So there will be eigenvectors C1 v1 vector and C2 v2 vector multiplied by their eigenvalues e to the power, right? This will be the solution. So how do we find the solution? We can write the matrix like this. We can find the determinant and set it to 0. That gives us a second order quadratic equation, right? We know how to solve it. So there's a trace here and there's a determinant. Trace is a plus d. So that's the trace. And the determinant is ad minus bc, right? And you can write down your solutions like so. Okay, very good. And the general solution looks like this. Do you have any questions, comments here? You remember this from the very first classes. So what we are going to do, we are going to now attack this problem. Okay, let's say you are given this x dot equals x plus y and y dot equals 4x minus 2. You can see that solve the initial value problem subject to the initial condition x0, y0 equals to 2n minus 3. Okay, so we need to diagonalize this matrix, right? How do we do that? Well, tau is minus 1. Why? Because it's minus 2 plus 1, right? Minus 2 plus 1. And delta is 1 times minus 2 minus 4 times 1. Are you following? So delta is minus 6. So lambda 1 and lambda 2 are given in terms of delta and tau like this. In the end, you get the eigenvalues. Do you remember how to get eigenvectors? You just plug them in and you are looking for vectors that satisfy this one equals to 0. For lambda 1 equals to, let me just write it. Lambda 1 equals to 2, the vector becomes 1, 1. Okay? For lambda 2 equals to minus 3, the vector becomes 1 minus 4. Okay? So what does it mean? Well, for this particular question, you can just, this means that the general solution is like this. But to find C1 and C2, do you remember what we need to do to find C1 and C2? Anyone who remembers the very first?
Initial conditions?
Yes, initial conditions are 2 and minus 3. So this is our f function, like f0, 2 and minus 3. Ooh. I'm saying something, writing something else. 2 and minus 3, right? Do you remember how to get C1? V1 dagger F0. Do you remember this? So if we do that, V1 dagger is 1, 1 times 2 minus 3. What do you get? Minus 1. Is that right? V2 dagger, I'm afraid this will be wrong, but let's trust in ourselves. 2 minus 3, what do you get? 14. Looks weird. Let's see. It's wrong? Is it wrong? Anyways, no worries. I'm sure there is a reason for it, but that's not the point. Yes, very good point. We are not orthonormal. This is not a symmetric matrix, right? Very good. So we need to go over this, solving actually these equations. And if you do so, you get C1 equals to 1, C2 equals to 1. Okay? That's not the point. The point is to draw this. This is a general thing. We have already done the solving part. Now we are approaching it graphically. So what are we doing graphically? So remember, lambda 1 was 2, and corresponding vector was 1, 1. What we do is we just plot the 1, 1 vector. This is the 1, 1 vector. Okay, and we notice that lambda 1 is plus 2. It's a real number and it's positive real number, okay? Which means that it will explode in that direction, okay? Because no matter where we start, we will have C1 times V1 times e to the 2 times t. So that vector is going to grow and grow, okay? What else do we have? We have lambda 2 equals to, let me use another color. Lambda 2 equals to minus 3, and the corresponding vector is 1 minus 4. So this line is the 1 minus 4 line, and the eigenvalue is negative, so it will be attracting in that direction. Okay? So this point in the middle where they cross, its behavior is determined by this lambda. Okay? And in this particular case, it's a saddle point. Saddle point. Do you remember saddle point? We discussed it in 1D, but in 1D it's a bit weird because it's attracting from one side, repelling from the other side. Not really a Pringles thing. This course is also brought to you by Pringles. Anyways, this is really Pringles, right? Because it's repelling in one direction, attracting in the other direction. So we figured out the general thing, and now since we know it graphically, we can actually solve the question also graphically. What was the question? 2 minus 3. Where is 2 minus 3? 2 is somewhere here, let's say. Minus 3 is somewhere here, so it's going to go this way. So we know graphically what's going to happen. Are you with me? Following? Yes? Okay. Very good. I have a code. for this one, here's the code. You have some function here, the x1 plus x2 and 4x minus 2x1. No, 4x1 minus 2x2. If we run this, it's going to start Pygame in a moment. And we will have the whole thing. Just give me a moment. Give it a moment. Okay, there it is. Yes. So, you see, this is the 1, 1 direction. This is the 1 minus 4 direction. Okay? And these red things are basically arrows. It tells you which way the system wants to go in every point. So you can see that if I start from here, I want to go there. If I start from here, I want to go there. Start from here, want to go there. Start from here. In either case, you end up in on the 1, 1 line. Just if you start on the right-hand side of this line, you end up there in the plus infinity, plus infinity. If you start on the left-hand side, you end up at minus infinity, minus infinity. Okay? So far, so good? Very good. Do you have any questions at this point? Yes?
Can I call this chaotic since?
No. Since?
Initials
No.
very sensitive.
Yes, very good point. It's very sensitive only there. Only on top of that line. Like if you are going to calculate Lyapunov exponent, okay, no, okay. The answer is really strictly no. Let me tell you why. So you start from here, you go there. You start from here, you go there. But your problem is you start from here and you start from here. They are diverging. So my guess is if you do Lyapunov exponent right on top of this line, maybe you can get something non-negative, maybe. But otherwise, all these points have negative Lyapunov exponent. They are all converging to the same place. But yeah, you have a feeling of chaos. I would give that to you. But when the real chaos comes, it will be chaos everywhere. No matter where you start, you will always be in a... I mean, the whole phase plane will be like a dough that is being stretched and compressed, stretched and compressed, stretched. And so no matter where you start and choose your 2 points, they will always diverge. Here,
Sensitivity will be
everywhere. Sensitivity will be everywhere, yes. And you will not converge to anywhere. There will be no place to converge. I had a poetic way of saying, what was it? You settle on something that never settles. Okay? Here you settle on something that settles. It settles, although at plus infinity. Yeah, it's a point. It's going there. Very good points. All right. Any other questions? So this is just one thing that can happen. Many things can happen. For example, what if both lambdas are negative, let's say, and one is smaller than the other one? Then you will have corresponding, let's say you have corresponding eigenvectors. They will be both attracting, right? But one will attract slower than the other one, depending on lambda, right? So for example, this is the fast eigendirection, meaning maybe lambda 2 is minus 4, let's say. Let's say this one is lambda 1 equals minus 1. Okay? The one with minus 4 is attracting faster than the other one, so it will reach. But in any case, this point will be a stable node. Stable node. Not mode, node. Okay?
And the shape of that is y equals x to the 4, right?
This is a general thing. Okay. Are you saying that because of this?
Yes. Because one of them go like e to the minus t and others e to the minus 4t.
I'm not sure. But at least here that was the case. Actually here it wasn't the case. So I don't think it is the case over here as well. So it's like e to the, they are both going with e to the minus t and e to the minus 4t. They are both going to 0. But you are saying that this is something like, we don't know the slope of that line. We just know the eigenvector.
But we know that if we take that line to be x direction, then that's...
Okay, you are saying that with respect to this being x, this is 4x.
Yeah.
I would get, maybe, yes. Okay. Probably you are right. So, what happens if the eigenvalues are complex numbers? So there is lambda 1 and lambda 2, and we have seen the cases where they are real numbers, right? Positive and negative. What if they are complex numbers? If the eigenvalues are complex, the fixed point is either a center or a spiral. So this is the center. Have we seen a center already? Yes, in harmonic oscillator, right? We haven't seen a spiral, I guess, yet.
Because we use that harmonic oscillators as well.
I think we did, but not in this context.
Oh, right.
We have already seen an example of center, it's simple harmonic oscillator. The origin is surrounded by a family of closed orbits. Note that centers are neutrally stable since nearby trajectories are neither attracted nor repelled. A spiral would occur if the harmonic oscillator were lightly damped. Then the trajectory would just fail to close because the oscillator loses a bit of energy. So complex eigenvalues occur when tau squared minus 4 delta is less than 0. Okay, in which case you have this kind of eigenvalues. So I will just skip all this and come to the point. This is what we should know by heart. Okay, this is the main point here. We can classify, we have seen saddle points. They are these points where one direction repels, the other one attracts. So this happens if delta is less than 0. Okay, just look at delta. If it's negative, then you already know what's going to happen. It's a saddle node. Okay. If delta is positive, but you are in this region where tau squared minus 4 delta is greater than 0, okay, so tau should be positive as well, then you have an unstable node. What does it mean? Unstable node means it's repelling in both directions, right? If you are over here, it's attracting in both directions. So you have a stable node. If you are right on this line, then you have centers, meaning that you go like this. Okay. If you are in this region, then you have a stable spiral. You are going to spiral in. And if you are over here, you have an unstable spiral. You are going to spiral out of that trajectory. Do you have any questions related to this? So that is the main graph, and I want to get a screenshot of it in case we need it. Okay. So, classify fixed point x equals to 0 in this system. What do? You find delta, which is 1 times 4 minus 2 times 3, which is minus 2. Since it's minus 2, it's what? Saddle node. That's it. That's the end of the problem. So that's how easy it becomes. For example, for this one, delta is 5 and tau is 6. So tau squared minus 4 delta is 16. So the fixed point is a node, an unstable node, right? Because it's somewhere here. Does it make sense? You may be thinking this is just something arbitrary. It's not, because we now have a general picture of 2D linear systems. And when we go to 2D nonlinear systems, we can use this linearization around the points to figure out what's going on. You can read these parts and get some idea about love affairs. Okay. It's actually a paper by Strogatz, and it's a lot of fun. What will happen with love dynamics? Okay. You can read it. Where are we? We are in phase plane. Are we doing nonlinear systems? Yes, we are doing 2D nonlinear flows. We are done with linear flows. So, again, this is the system we are dealing with, and this time f can be nonlinear. Okay? For example, consider this system. Use qualitative arguments to obtain information about the phase portrait. Okay? Is it a nonlinear system?
Yes.
Why? E to the minus y. Very good.
But we can reduce to a single linear equation.
How?
Yeah, y does not depend on x, so we can solve for y and then substitute y, and it is just a linear non-homogeneous system.
Shouldn't be. Let's read the book.
Yeah.
First, we find the fixed points by solving x dot equals to 0 and y dot equals to 0 simultaneously. Okay. The only solution is minus 1 and 0. Let's put it down. X equals to minus 1, y equals to 0. Does it satisfy both of them being 0?
Yes.
Yes, it does, because e to the minus 0 plus minus 1 is equal to 0, and minus 0 is equal to 0. Very good. To determine its stability, note that y going to 0 as t goes to infinity, since the solution, this is what you are saying, right? Blah, 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 blah. This is more important. To sketch the phase portrait, it's helpful to plot the null lines. Okay, what are they? They are just lines defined as the curves where either x dot equals to 0 or y dot equals to 0. Are you following? Yeah. So What is x dot? Let me just rewrite our equations. I will do it a couple more times. For this one, the null line is y dot equals to 0, which is when y is equal to 0. Is that right? So the whole x-axis is a null line. Okay. For this one, it's a more complicated equation, which is just x plus e to the minus y equals to 0. Okay. It's like e to the minus e to the minus y, but drawn like this. Here it is. Okay. We have it plotted already. So let me remind you, this is where y is equal to 0. That's why it's x-axis. And this is where x plus e to the minus y is equal to 0. Now, what do we know about this line? We know that x dot is 0. What does it mean, x dot being 0?
X is constant along that line.
No matter where we are on top of this, we have to have a perpendicular trajectory because x dot is not changing. So x is not changing on top of that line, which means that you are either going up, straight up, or you are going straight down. Yes or no? You can't go sideways, you can't go right or left because x dot is 0. Let me give you time to sink in. Amna, yes? Yes. So why the arrows here are pointing down? Because once you pass through this point, which is, can you tell me where that point is? That point is at x equals to minus 1, right? This is x equals to minus 1. If you are to the right of x equals to minus 1, then what happens to y dot?
If I'm at right, then it's y that equals minus y. I don't know.
You don't know? I thought you knew everything. So
It's still 0, so y that must be 0 again.
let me remind you, y dot was minus y, right? If I'm at the right, actually it depends whether I'm on the top or at the bottom of y-axis. If I'm at the top of the y-axis, minus y, so I point down. If I'm at the bottom, minus y is positive, so I'm pointing up. Is it making sense to you? Yeah. Yes? Good. How about the null line, the other null line? We know that on top of this line, I have to go horizontal. Why is that?
Because y's derivative is 0.
Y derivative is 0. Do you agree? Very good. So whether I'm going to the right or to the left depends on whether I am on the right hand side of x equals to minus 1 or left hand side. If I'm on the right hand side, then this becomes positive. So look, this is, let me think, x is greater than minus 1 here. First of all, y is 0, right? Y is 0 on top of this, so e to the minus 0 is 1. And if I am greater than minus 1, this one plus this one is greater than 0. So I'm pointing to the right here, and I'm pointing to the left here. Okay? So slowly you get an idea of what's going on. Like trajectories want to go down this way and want to go this way. And trajectories over here, some of them come and go that way, but some of them come and go this way, some of them go this way, etc. Okay? You get a picture of the whole thing. Although it was non-linear, you start getting a picture of it.
Find out the direction on the x-axis. Like one is going this way, the other is going this way. I didn't understand that you did on the top.
You mean this one?
No, on the x-axis. Around the...
Okay. You want to understand this one again, right? This one.
Yeah.
Okay. Let's be more precise. So if I am over here, I am definitely at y equals to 0, but I am also at x greater than minus 1. Right? So x plus e to the minus y is equal to x plus e to the 0, which is equal to x plus 1, which is greater than 0 because x is greater than minus 1. So what was this? This was x dot. X dot is greater than 0. Very good. Thank you very much. Very good. If you want to see this in a computer, I have a bad code that shows this. MATLAB. Just ignore this line, okay? Look, wherever you start, we basically have these lines over here. And this whole thing looks similar to what we have in the book, right? Okay, very good. But the next examples will get more and more important. So this is important, fixed points and linearization. Do you have any questions at this point? No? Okay, so we have a general system that is in general nonlinear, right? F and G. Now, if you have a fixed point, it means that both f of x star y star and g of x star y star are both 0 at the fixed point. So we can linearize the system around the fixed point, just like we did in 1 dimension. This is now 2 dimensions. What do? Taylor expansion, the usual thing. And you end up with these kinds of equations. Let me show you here. So this is for u dot, which is now shifted x. We have shifted to x star, and u is x minus x star. V is y minus y star. So if you write and linearize and ignore the quadratic terms, do you see what you get? You get a 2D linear system. Should I repeat what just happened? So we saw a nonlinear system, right? There was a fixed point here. Now we get closer and closer to that fixed point, and in that close vicinity, it is basically a linear system. That's what we are doing, okay? So we are linearizing this part, and if you are thinking that these are functions, they are not. They are numbers, because this whole thing is evaluated at x star, y star. So we evaluate del f over del x, del f over del y, del g over del x, del g over del y, all of them evaluated at x star, y star. So they are just numbers. Okay, which is called, maybe you have heard of this, Jacobian matrix. Yes. In other contexts, you have heard of it. There are some effects of small nonlinear terms, let's read it really quickly. Is it really safe to neglect the quadratic terms? In other words, does the linearized system give qualitatively correct picture of the phase portrait near x star y star? The answer is yes, as long as the fixed point for the linear system is not one of the borderline cases. What do we mean by borderline cases? Is this. If I go to desktop and this screenshot, you shouldn't be over here or over here or over here. I mean, if you are here, 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 then linearization works. Okay?
Can you not linearize on borderline?
You need to include the higher order terms then.
So at that point it's not negligible?
Yes.
In borderline cases, we have 1, 0 eigenvalue, right?
Okay, let's see. For example, here, actually, what does delta equals to 0 mean, for example?
That equals
AD equals BC. Okay, there is also the eigenvalue equation for tau and delta. Let me see.
that is just product of eigenvalues.
Delta is product of eigenvalues. Then, for example, that borderline, one of them at least has to be 0. Yeah. So there are that kinds of things happening. Okay. Find all the fixed points of the system x star x dot equals minus x plus x cubed. This is nonlinear, right? And y dot equals minus 2y. Okay, fixed points occur when x dot is 0 and y dot is 0. Hence, we need x equals to 0 or x equals to plus minus 1 and y equals to 0. Why? Because minus 2y equals to 0 gives you just y equals to 0. Minus x plus x cubed equals to 0 gives you x parentheses minus 1 plus x squared equals to 0. So x could be 0, x could be plus minus 1. Is that right? So 3 fixed points, 0, 0, 1, 0, minus 1, 0. And you can find Jacobian. This is a general point xy, for a general point xy. How did we find it? We took the derivative of, so f is minus x plus x cubed, g is minus 2y. So what is del f over del x? Minus 1 plus 3x squared. That's written here. Del f over del y, 0. It's written here, etc. You understand it, right? So now, for example, at 0, 0, the Jacobian is this. So where are we with this Jacobian?
It's a stable sink.
It's a stable sink. How did you get it?
Two negative eigenvalues, minus 1, minus 2.
Exactly. Do you understand it? Or,
Delta 2 is less than lambda 1, which is less than 0.
exactly, that's the case. And delta is 2, tau is minus 3. So we are over here. Okay? I didn't do the del squared something calculation, but we are here. Etc. You know, you can understand these systems. And if you draw it, if you plot it, this is the, which one did we do? We did the 0, 0, and it's a stable sink, as you can see here. The others turned out to be saddle nodes. Okay, very good. Are we going too quickly?
No.
That's the correct answer. Okay. Rabbit versus sheep. This is a typical classic Lotka-Volterra model of competition. This is how it is given. So let's read this. Each species would grow to its carrying capacity in the absence of the other. This can be modeled by assuming logistic growth for each species. You remember the logistic equation. So for each species, you can see there is a logistic part, right? But then there is a predator here. Okay, rabbits have legendary ability to reproduce, so perhaps we should assign them higher intrinsic growth rate. So that's why this is 3. The other one is 2. When rabbits and sheep, this is, by the way, a system where 2 animals are competing for one resource. Okay, I just said predator. There's no predator here. Okay, this is predator-predator system, and prey is grass. Okay. When rabbit and sheep encounter each other, trouble starts. Sometimes the rabbit gets to eat, but more usually the sheep nudges the rabbit aside and starts nibbling on the grass. Well, assume that these conflicts occur at a rate proportional to the size of each population. If there were twice as many sheep, the odds of rabbit encountering a sheep would be twice as great. Furthermore, we assume that the conflicts reduce the growth rate for each species, but the effect is more severe for rabbits. So that's why this is 2, while this is 1.
I have
Yes.
a question.
Sure.
If this was a wolf-rabbit system, then would it be y derivative equals y times 2x minus x plus y? Sorry, 2x plus x minus y?
Maybe. Yes, probably. I don't know if we have predator-prey system. I don't think we will do it, but yes. This is a little bit a sad model, as you will see at the end. Either rabbit or sheep dies. Okay, let's exercise. Let's see what's going on. So we have, for example, 0, 0 is a fixed point. Do you agree? Because that would result in x dot equals to 0, y dot equals to 0. What else? We have 0 and 2. So just, the book solved it for us. So we have 3, 0, and we have 1, 1. Do you have any problem with this? Just the derivatives. Then you can just plug in these values, right? And you are going to get the behavior at each point. For example, 0, 0, which corresponds to 0 sheep and 0 rabbit, is an unstable node. Do you remember we had the same unstable node for one-dimensional system? We had something like this, and if we had only a few animals, it would grow to the carrying capacity. Now it's seen in 2 dimensions. So if you have a few rabbits, few sheep, they will grow. Okay. 0, 2 is when you only have you only have sheep. Okay. That turns out to be a stable node. Okay. So we have a stable node here, an unstable node here. So starting from here would take you here, probably. 3, 0 is all rabbits, no sheep, right? That's here. And if you start, if you start here, you go there. But if you start here, you go there. Okay? And then there is the saddle point. Saddle point could be a nice solution where you have both rabbit and sheep. Okay? But unfortunately, it's a saddle point. So if you start from here, you go here. If you start from here, you go here. Start from here, you go there. Start from here, you go there. Okay? You might say, how come we have rabbits and sheep in nature? Because the model is much more complicated. There is the McDonald's, old McDonald's. It's taking care of them, right? Okay, the whole thing looks like this, and as you can see, we are now applying what we have learned from linear systems to nonlinear systems. This thing, Abdul, that you said, you start from here, it goes there, start from there, it goes there. These things are called basins of attraction. Basin, this is the boundary of the basin, and if you start from here, you will end up here. If you start from here, you will end up there. But if you start from here, you will end up there. If you start from here, you will end up there. And this is a like boring basin of attraction. Okay, this stuff can get much more complicated in different systems. I didn't mention this, but if you are interested, you can look at Newton's fractal. Looks like this. Say it again. Yes, but that's a deep subject. Okay, finding Mandelbrot inside this is a deep subject. But just by itself, you know how there is Newton-Raphson method to get the equations the correct answer. So let's say your question is x cubed minus 1 is equal to 0. Okay, what is the solution? 1, right? But there are also two complex solutions. So if you start around here, you will end up here. If you start around here, you will end up there. If you start around here, you will end up there. But then in the boundaries, you have all kinds of fractal shapes. There's a very nice video where 3 blue, 1 brown, where he finds a Mandelbrot set. But to find Mandelbrot set inside this, he takes a lot of effort. But the point is that also in that video it's mentioned that there can't be a boundary with only 2 colors. Okay, here you have a boundary with only 2 colors. In here there can't be a boundary with only 2 colors. That's why it has to go to infinite detail. Okay? That's one of the reasons. And you can show that there can't be 2 boundaries. Oh, very good. We are doing very good. Just 1 minute left, so let me show you rabbit and sheep. This is the system. You start from here, you go to all sheep, start from here, all rabbit, start from here, all rabbit, start from here, all sheep. Okay? Any questions? Just playing with it. Let me also smile, so this is the cover. Okay. Any questions? No? Say it again. Very good. Okay, let me stop.